Okay, so the final part of forces and friction, chapter 7, is connected particles. So basically we are now looking at a pulley system. But we're not just looking at any pulley system, we are looking at a pulley system that now involves inclined planes and friction, okay? So they are starting to get quite a bit more challenging. This will, again, it'll probably increase the number of unknowns. So in a question like this, what you've got to think is, I might need to set up some simultaneous equations, which is exactly what you're going to need to do in the majority of these questions. So two particles P and Q of masses 5 kilograms and 10 kilograms respectively are connected by a light, inextensible string. The string passes over a small, smooth pulley, which is fixed at the top of a rough, inclined plane. So the pulley system is always going to be smooth, but the plane, the surfaces they are on, may end up being rough. P rests on the inclined plane and Q hangs on the edge of the plane with the string vertical and taut. So I've now got a bit of additional information where I can draw my pulleys. So I've got P here, which is 5 kilograms, and I've got Q here, which is 10 kilograms. I know it's a rough plane, but we'll sort that out in a minute. The plane is inclined to the horizontal at an angle of alpha, where tan alpha is 0.75. So again, it's really useful they've given us that, because it's one of our Pythagorean triples, so we are easily able to work out our sine alpha and our cosine alpha. The coefficient of friction between P and the plane is 0.2. The system is released from rest. So before we start, let's add on all of our forces. Because there's quite a few, I'm actually going to mix up my colours, I think. Make this a bit more interesting as I'm doing it. So I've got the weight of my mass Q, and I've got the weight of my mass P. I have tension in the string. Tension does go both ways, but at the moment we kind of want it in relation to P and Q, rather than all, but we've just got to remember later on, potentially, that tension also goes the other way. I've got a normal reaction from where P is resting on the plane. I'm also going to have friction acting this way. I'm not going to add in another unknown. I'm going to use my coefficient of friction to write it as 0.2 R. Now, because it's released from rest, I then know that my system is going to accelerate up the pulley like that, and Q would also be accelerating down like that. It's really important that we remember acceleration is on both parts. And because we've got a taut, inextensible string, we know acceleration is the same throughout. Okay, so while they're still connected against the pulley, while the string is kept taut, then it has to be acceleration equal throughout. Again, likely I'm going to have to resolve some forces somewhere, so sometimes it's useful to just draw these in straight away. Okay, so A says find the acceleration in the system, so we want to find A. So I can find A if I'm looking at particle P as a separate system. I can also find an equation for A looking at Q as a separate system. So remember, connected particles can be seen as a system as a whole or as two separate systems, and in this case we are looking at them as two separate particles. So I'm just going to deal with P for now, and I'm going to resolve parallel and perpendicular to the plane. So I have tension pulling particle P upwards, and I have friction pulling the force the other way, and I also have the weight of particle P, and that's equal to mass times by acceleration. I'm now going to resolve perpendicular. So I've got, again, there's no perpendicular movement, so I can just equate them. So R is equal to 5G cos alpha. Going to combine these together. Obviously, I don't want as few unknowns in one equation as I can. So I'm going to substitute R into my first equation. So T subtract 0.2 lots of 5G cos alpha, subtract 5G sin alpha is equal to 5A. Now, because I have cos alpha and sin alpha, I'm going to neaten this up a bit now, just so that it's done and I don't have to worry about it later. And if I substitute these into my calculator, given what I know, I'm going to leave it in terms of G still, because then it leaves things much more accurate and not having to write lots of decimal places. So I end up with T subtract 19 over 5G is equal to 5A. Now it wants me to find the acceleration of the system. It doesn't want me to find it in terms of T and G. It wants me to find what it is. So I'm going to have to interpret more information in my question. I've only looked at particle P, so I'm now going to look at particle Q as a system in itself. So I'm just going to do that here, so I'm using a bit more of my paper more efficiently. So Q means I'm only looking at this bit here. So Q is moving downwards, so I'm going to resolve at Q vertically with the movement downwards as positive. So 10G subtract T is equal to the mass 10 times my acceleration, A. So now I have two items to compare. Now I want to solve for A, because I could easily multiply this one by 2 to make it 10A equals, and then find a solution for T, and then substitute it in for A. But if I don't have to find something else first and I can go straight for A, then I will do. So I'm just going to rearrange this to be 10G minus 10A equals T, and this to be T equals 5A plus 19/5 of G. So now I have two equations for tension, which eliminates tension and leaves me with only acceleration. So therefore 10G minus 10A must be equal to 5A plus 19/5 of G. So I end up with 15A is equal to 31/5 of G. So A is an exact answer. It's 31 over 75G, but it wants a value which is 4.05 metres per second squared to 3 significant figures. Now the second part of the question is find the tension in the string. Find the tension in the string. Well, now I have my value for A, and I have a couple of equations that I can use to find T. The one I found easiest, just because I can't be bothered to deal with more fractions when I have a whole number, is T is equal to 10G, subtract 10 lots of 31 over 75G. So I'm obviously using my more simple equation and my more accurate answer for acceleration. And this gives me 57.5 newtons to 3 significant figures. Okay. Final example on the forces and frictions chapter. So, one end of a light, inextensible string is attached to a block A of mass 2 kilograms. The block A is held at rest on a smooth fixed plane, which is inclined to the horizontal at an angle of 30 degrees. So I'll draw my A and B. There will be a pulley system, so I'm just getting that ready. The string lies along the line of the greatest slope of the plane and passes over a smooth light pulley, which is fixed at the top of the plane. The other end of the string is attached to a block B of mass 5 kilograms. The system is released from rest. So let's add in again all of our forces before we even start approaching the question. So I've got weight 2G, I've got weight 5G. Obviously, we have to assume the pulley is going to move this way. We always have to follow which is heavier. They'll never ever say which way it moves. You just have to understand that that is what's going to happen. So there's a normal reaction where A is. There's tension in my string. And there is no friction. It is a smooth plane, so we're not worrying about friction this time. What I have got is I've got acceleration up the pulley that way and acceleration vertically down that way. Again, my resolving forces, which I'll probably need at some point. So, part A, show that the acceleration of the block B is 4/7 of g. So this all implies that acceleration is the same throughout. Because if I'm just looking at block B, I haven't actually got enough information to solve for A. So I do need to use information about A as well as about particle B. So I'm going to deal with particle A first. It's not my part of my question. AI. Okay. So I'm going to resolve parallel to the plane first at particle A. So I've got T pulling it upwards, and then I've got the weight of block A down. I haven't got friction this time, and that's equal to mass times acceleration. I know sine 30 is a half, so if I don't have to leave trig in, I'm not going to leave trig in. So tension subtract gravity is equal to 2 lots of acceleration. I don't need to resolve perpendicular to the plane. It's not going to help me in this case. So I'm just going to go straight to, and I'm not going to mess up my colours, I'm not going to use my pinks, otherwise that'll be confusing. I'm going to resolve vertically at B. So 5G is putting it downwards, tension is holding it back up, and that is equal to mass times acceleration. So again, I can make T equals here and T equals there. So I've got equation 1 and equation 2. For 1, T equals 2A plus G, and for equation 2, T is equal to 5G minus 5A. So therefore these things must be equal to each other. So therefore 2A plus G is equal to 5G minus 5A. 7A is equal to 4G, so therefore A is equal to 4/7 of G as required. I think it's something like a little box that Miss Goddard taught you, which basically shows that you've shown it as required. Apparently she said it's less pompous than writing QED or as required. Less pretentious, that was the word she used. So I think it might be a little box, but I can't remember, so you might need to message me and tell me what it actually is. But I've put a little box for now, and if it's wrong, then one of you guys can correct me at a later date. Okay, so we've shown the acceleration. The next part, find the tension in the string. Well, we're just going to substitute this value into one of our other values. For tension, I prefer addition to subtraction. So I'm going to choose equation A, which is 15/7 of G. But actually it's quite a nice solution. It's exactly 21 newtons. So that is quite nice, actually. Don't often get a whole number for a lot of our values. Okay, part B. So part B I'm not going to write down. So you need to listen, just because otherwise you're watching me write down a load of words. So it says, state how you've used the fact the string is inextensible in your calculations. So actually the fact it says the word calculations in this context is really, really important. Because we've used the fact that it's light and inextensible in the sense that we know that there's tension, but we've also used it in our calculations to know that acceleration is equal throughout. It's another reason why I'm not writing lots of words, because my handwriting is rubbish. But we have to talk about the fact that its acceleration is equal throughout, because that is what it's relating to, and it says how we've used it in our calculations. Because it's not just the fact that we've also incorporated tension. So that part is really, really important. And it doesn't often word it in that way to emphasise that point in particular. Okay, part C. Calculate the magnitude of the force exerted on the pulley by the string. So, I've got my pulley here. Now my string it's pulling tension in that direction, and it's pulling tension in that direction. So the resultant force that is as a result of those two tensions has to bisect those two forces. So that is the resultant of my force. It will be in the middle. So if you imagine two vectors going off in two different directions, the resultant vector does effectively travel through the middle. And that is what is happening here. So that is my attempt to draw theta, and it's quite small. They're both theta. We need to work out what those angles are, because we can form right angle triangles like we have, where tension is the hypotenuse. So if I created a right angle here with tension, we can imagine that these meet at this point here, even though I've obviously drawn it at a bit of a curve. It is meeting at a point if we pulled those back formally. Okay. Now, what is that angle? Well, we can use our information about parallel lines. If in doubt, it's the same as this one, okay? Which in this case it is. So if you imagine I drew a horizontal line here, I know that this angle is 30 degrees because of alternate angles. This line here, that is tension, is parallel to this line. So if I were to draw a horizontal line there, I know that that angle would be 30 degrees because they're parallel to each other, so it's going to be the same. So this would have to be 60 because these vertical and horizontal obviously create a right angle. So if I'm bisecting 60, then theta must be 30 degrees. So if in doubt, if you're really not sure, if you can't work it out, if you can't visualise angles in parallel lines, always use that value. So my resultant force, well, it's going to have a force dictated from tension 1 and 2. I know they're the same, which is fine, but it's just so I can show you how I'm approaching it. So the resultant force here is going to be tension cos 30. And the resultant here is going to be tension cos 30. So therefore the overall resultant is 2 lots of tension cos 30. Now we have a value for tension. The book uses 15/7g, but like I said, it's actually exactly equal to 21. So R is 42 cos 30, which if we put into our calculator is 3.71 newtons to 3 significant figures. So that was probably the hardest type one because you have to actually visualise where the force is. We're talking about the force exerted from the string on the pulley by the string. So what force is the string pushing on the pulley? And it's the result of these two tensions. Remember, tension already takes into account the weight of both parts of the pulley. So tension is the same throughout. I know it's quite a difficult concept, but because tension is working in both directions, it is taking into account both weights. Okay? I personally think that these kind of questions are the hardest questions that they have out there. Projectiles can sometimes get a bit more challenging, but we will see that when it comes to it. But I just want you to do lots and lots and lots of practice of these questions. I will give you a full applied paper when I can, so that you've got these exam questions, but I'll try and get some exam questions prepped for you in advance of that as well, so that you've got lots of practice that you can be doing.